Okay, everybody okay with the homework? No problem? So the idea, I guess, was to converge on the F equation, not on the theta equation, because if you, right, did you try that?
Yeah.
Did it work? It should, yeah, right, because it's the F equation that you're solving. So it is not the number of significant digits in the first case for the root, or for the missing derivative for the theta equation. So that should work out okay. Okay. So remember, one of the equations completely defined as an initial value problem, right? The theta equation, because we have both theta and theta prime as given on the left boundary, and what is really missing in the problem is the second derivative of the f, that's the velocity of the string function equation. So if you do that, it should work out okay. Okay.
When will the next one be posted or due?
But there's probably by tomorrow I'll post it. Okay. So I'm going to talk about that, one of the problems right now. Go ahead.
And it will be due next Thursday then? Or?
Yeah, I think so. Yeah. This might be. I'm really sort of thinking about, you know, what the homework equation would be. It is a little bit more than what I'm planning now. I'll give you more time. Okay. So let me see. Okay. No, I don't have my.
You with the pen?
Yeah.
It's next to Skype. You see that?
Where?
Up.
This? No, not this.
Up.
Okay. Oh, okay. All right. Great. All right. Thanks. Okay. Now, there's an interesting. This is what I'm going to talk about now is very similar to the home assignment. At least one of the home assignments that I will pose. So suppose we have a higher order equation. Okay, just like one of the first equation that you saw. Okay. Order equations. And still we're looking at boundary value problems with ordinary differential equations. Okay. So this is a very classical equation. It's called Blasius equation. And it entails all the simplifications or conversions into ordinary differential equation from partial differentials, and also the similarity assumptions. The idea, remember, is that if we have a problem that can be described in terms of a similarity variable, right, we can sort of convert the governing partial differential equations into a system of ordinary differential equations, most of the time higher order equation. Nevertheless, the Blasius equation defines the structure or the velocity distribution in a boundary layer if there is no pressure gradient, more or less, on a flat plate. Okay? And you do start with the partial differential equations that govern the flow. I'm not going to bother with those. All right? So those are nonlinear partial differential equations for momentum, the x direction momentum, the v direction momentum, and also the continuity equation. So pretty complicated equations. So we do two things. One, self-similar, or start with fundamental equations. Which are mass and momentum conservation. Assume excuse me, two-dimensional flow, incompressible, basically means density and all the physical properties of the fluid would be constant, and steady. Okay? These are definitely restricted conditions, but still applicable to a very wide range of very practical flow situations. And then we seek for, oops, let me write this. All right. Seek for self-similar solutions. Now, if we assume the flow two-dimensional and incompressible, we can replace U and V with a stream function, okay? That automatically satisfies continuity. And if we look at for self-similar solutions, we can take the X and Y variables and embed them into an equation for eta. Now, the psi equation, we write it then as some sort of a function of eta, so that f prime, you've seen these before, so that's why I'm sort of bypassing it quickly. F prime then will be equal to u over some u infinity, and the typical geometry that we're looking at would be a flat plate, and there's a velocity or flow coming in, and once it hits the this is uniform velocity, then it, because of the viscous effect between the, or friction effect between the plate and the fluid, it sets up what is called a boundary layer. So this would be the u velocity profile. Okay, u of y. So this is x, and this is y. Okay? So obviously u is a function of, actually it is both a function of x and y. Right? Oh, sorry about that. Right, whatever. So this is u, a function of x and y. Right? So we make the u, x, and y converted into an f, which is a function of eta only. So what then we obtain is we have one equation with one unknown, which is f of eta, okay, and f of eta, well, I mean, then u over u infinity, or u1, this is u1, right, or u infinity, call this, u over u infinity, then is simply equal to a function of eta. Okay, so that's the main story with this thing. So after everything is said and done, a lot of algebraic manipulations and chain rules and whatnot, what we obtain is an equation that looks like f triple prime plus 1/2 f double prime is equal to 0. This is incredible, isn't it? I mean, you take all those equations and make some very physically valid assumptions, and then you obtain an equation which is so simple and sort of a doable equation that still will give you a very reliable and verifiable profile for the boundary layer. So I guess it's a sign of genius that somebody is able to see through this thing and get this equation. So this is called the Blasius boundary layer, Blasius equation. All right, so obviously we need boundary conditions for this thing, right? The first boundary condition is f of 0 is equal to 0. The second, f prime of 0 is equal to 0. So both of these boundary conditions satisfy continuity. And then the third boundary condition is f prime of infinity, right, is equal to 0. Of course, then we have to, like in the previous homework assignment that you've done, we have to replace infinity with a finite value. For these are for laminar flows, by the way, okay, not turbulent. So if the flow is laminar, generally 8 is equal to 10 is a pretty good guesstimate for the values at infinity. Okay, so this is then the problem at hand. So we have two boundary conditions on, let's say this is a, when these are of course on eta, right? The variable is eta. So when eta is equal to 0, y is equal to 0, right? So we have two boundary conditions on the wall. And one boundary condition on the free stream. So these two satisfy the continuity and no slip, okay, I should say. No slip. Continuity and no slip. No slip essentially is a condition that makes the velocity of the fluid that's in contact with a solid surface to be equal to the velocity of the solid surface. If the plate is not moving, of course, I mean, even if this is a wing section or something, you can assume the wing to be steady or stationary and the flow coming towards it. So then it has to comply with whatever velocity this thing has. Was there a question? Yeah.
Yeah. So I'm trying to wrap my head around the second boundary condition there. Doesn't that
F prime?
Yeah. Doesn't that state that the velocity doesn't change at the wall?
Yeah, the velocity doesn't change at the wall. That's correct. But the gradient of the velocity will change at the wall.
The slope of the velocity is huge.
The slope of the velocity is f double prime, right? This is stream function. So velocity is given as f prime of eta. So on the wall, it does not change.
F prime of 0 is the no slip condition.
That's correct. And this thing satisfies the no slip condition on the wall by using continuity. So, okay, for the v velocity. So this satisfies the u velocity, the no slip for u. Pardon me?
Wouldn't that be 1? Wouldn't f prime be equal to 1 in infinite distance from the...
Oh, yeah, this one is 1. That's correct. Yeah, okay. Sure. All right, thanks. Okay, all right. So to cut the story short, then we have an equation, right? A boundary value problem, f triple prime plus 1/2 f double prime is equal to 0. F of 0 is equal to 0. F prime of 0 is equal to 0. F prime of, let's call 10, is equal to 1. Okay? So these are the three boundary conditions that we have. So let's suppose that instead of using a shooting method, we want to solve this problem using finite differences. Okay? Solve the problem using finite differences. Okay. Well, of course, you can generate finite differences for third-order derivatives, but then stuff starts to be a little bit too convoluted because now the stencil or the computation molecule that you're going to use will have more points, 5 or 7 points, which basically means you either have to shift to one-sided derivatives for higher-order differentials, or you have to invent some boundary conditions outside of the physical domain, so neither of them will work. So generally for this kind of problems, you separate the equation, or you write the equation system of one second-order equation and one first-order equation. So we can say u, right, is equal to f prime, well, which is not a bad symbol because actually u is defined as f prime. So this then is your first equation. Then your second equation will be u double prime, right? Plus 1/2 f, we can't do much about it, times u prime is equal to 0. Okay, so this is the first order equation, and it needs one boundary condition. So this is a f prime, right? Let me clear that. Oops. All right. Or we can translate these into the new variables, right? This will be still f of 0 is equal to 0, but then we have u of 0 is equal to 0, and u of 10 is equal to 1. So this equation then we solve with f of 0 is equal to 0, and this equation we can solve u of 0 is equal to 0, and u of 10 is equal to 1. All right, so you know how to discretize that equation, right? You can apply finite difference second order, and on this one first order, collect terms, and get an equation which will have some coefficient, right? A, B, C, and so forth. But of course, the problem is with this term, right? Which makes it a nonlinear equation. Well, if you look at the original equation, of course it's a nonlinear equation too, right? Because it's a product of the variable and the second order derivative, so that's also a nonlinear equation. So you can't really get rid of the nonlinearity of the problem. So this is a nonlinear equation. Well, which basically means the finite difference equation, okay? Let's say apply second order finite differences, which will have nonlinear coefficients. This will also be a nonlinear equation. Difference equation. Okay, so the trick here is then to solve these problems in two ways. You can solve them in fully coupled way. All right, you can fully couple them and obtain a large matrix that would have unknowns, right, that will comprise of f and u. Or that of course complicates the problem a little bit. Then you either have to use a block tridiagonal solver, or the length of your solver will be quite substantial. Or you can solve this iteratively. And this is a very efficient way of doing the problem. Actually, you can go back to your original problem from last week, or from the last home assignment, right, and use it exactly in its given form by converting the first third order equation into a system of one second order equation, one first order equation, and leave the energy equation, the third equation as is because it's already the second order equation, and then solve those three equations sequentially. And these things converge very rapidly, okay? The good thing about this, of course, I mean, using finite differences to solve this system is right here, you are imposing the boundary conditions on the left and right boundaries right at the same time. So there's really no iteration on the boundary conditions or a missing derivative or something, okay? There is only an iteration because the problem has nonlinear coefficients. So what you can do is the following. Okay, let's call this equation 1, and this is equation 2. Assume a distribution, for u as a function of eta. Okay, well, we know the initial value, right? We know the final value. Well, you can assume it's something like this. Start with a straight line. Okay, we know at the left boundary, right, this is 0, at the right boundary it's equal to 1. So call this u, this is eta. We know that this is equal to 1. This is equal to, this is equal to 0, right? So this was your initial distribution. 2, using Euler. Even Euler method will work very efficiently, okay? Using Euler method, solve equation 1 for f. Right? So you've simply use up one-sided, let's say, with one-sided differences. Oops. Forward. Well, it's not too bad because you know the value of f on the left boundary, and then you know the distribution of u, right? If you discretize f prime by one-sided differences, you can step it up very easily, point by point, starting from the left boundary, which you know, and then cat it from the difference equation. Okay? Number 3, solve equation 2 with f from equation 1. So you basically then, you're lagging, right, the value of f as is coming from the previous guess. All right. So the first one is going to give you f at n. Well, this one is going to give you u at n plus 1, n being the iteration index. And this equation, of course, you're going to solve. I mean, you can solve it iteratively within a little do loop in itself, but the best way to solve it would be using either either the Thomas algorithm or the LU decomposition. In this case, LU decomposition is not a bad idea because it is an iterative solution, right? And you're going to change the right-hand side of this equation according to what you obtain from the first equation. So, but the issue is that this should converge with about 5 or 6 iterations to some value which is about 3 or 4 orders of magnitude less than the original error. Okay? And check convergence. Okay? Okay. Which is some error epsilon, or let's say some error norm. Oops, what's this? All right. So let's call this some error norm. F, so maybe maximum norm. Condition if less than epsilon. Okay. And you want to make this less than about maybe 3 orders of magnitude less than the original error. And if yes, solution converges. Solution converged. If no, go back to equation 1. But as I said, this is going to converge so fast, maybe our 5 or 6 iteration is not even worth writing any logic statement there. Just make the loop counter equal to about 10 or 20 at the most. You still will get a pretty good solution at the end of this thing. So this is a very powerful method. And if you have the original problem that you had, right, the or last week's problem, what we have is some f prime plus whatever it is equal to 0. Then we have theta double prime, right? That's equal to 0. So then, again, we convert this into a u prime equation, and then, or u double prime equation, right? U double prime. So this converts into an equation for u prime and f double prime. And then this equation you solve for theta double prime as it is. So these two, finite difference, this may be an Euler method. Okay. And yet you just sweep through these things, right? So then this is replaced. This is replaced by an equation for u prime. And then we have an equation for f double prime, just like the previous one. Now we have three equations. Again, make a guess on u prime and solve for f. Using that, solve for theta, come back and do the same thing. Okay, does it make sense? Okay. So I'm going to give you a problem very similar to this one. Maybe the thing to do would be to give the same problem that you worked on last time and ask you to use this method. How about that? Good? Because you now know the answers and you know exactly what you're looking for. Okay. How do I get out of this thing? Oh, okay. Now, a couple of things. There are several typos in my notes about the ODs, and I corrected them. So now what you have there is the corrected version. And let me go very quickly over a few of those points so you know what I'm talking about. I think as one of you pointed out, one of the areas really was in the Thomas algorithm, you know, do loop counter. So I did correct that one. Okay. All right. One was on page 13. All right. To page.
Is that with the superscript?
Yeah, superscript subscript each, yeah. Page 13. Right. Oh, okay. So yeah, this one, right? This one I corrected to superscript n represents the iteration index. Okay. Then I added the definition of, right here, definition of, what is that now? Okay, of xi, which is really phi I n plus 1 minus phi I n. Then
but these are not the corrected notes.
These are not the corrected notes. I'm just showing you where I corrected them. Okay, the corrected notes are posted. Then we had on page 23, I'm showing you the errors so you know what I'm talking about. Okay. Page 23. Okay. All right, here I have I was missing. So this really belongs to this section, and I have a new definition of J here, which is really as J goes from n minus 1 to 1. Okay, so it goes backwards. So in the first step of the back substitution, we go from the top. In the second, I'm sorry, in the elimination process, we go from the top, and in back substitution, we go from the bottom. So make sure that these are corrected there, okay? And then there was the definition of this matrix. These should be your B's, okay, B2, B3, B4. And what else? There's a minus sign on page 30. Right here, there should be a minus sign. Okay. And finally, to be consistent with my previous notes on page 33 and the subsequent pages, I changed the definition of the subdiagonal and superdiagonal. So these should be B's and these should be C's, which are such in my notes now. And the superdiagonal is C and subdiagonal is B, so there's really no discrepancy between those. Okay? All right, do read some of these things when I'm talking about the implementation of the boundary conditions. Now, one thing I want to quickly go over is okay. Okay, then go back to this thing again. All right, let's say one-sided differences. Okay, now remember when we have a derivative boundary condition, right? Let's suppose we have derivative boundary condition at this end, right? So right here, let's say we have the x is equal to 0. So this is my boundary point. This is my first point away from the boundary, and this is my second point away from the boundary, and so forth. So call this I is equal to 1, 2, 3. I is equal to 1 is the boundary point. Okay, so the derivative actually, of course, has to be evaluated at the boundary point. Du dx I is equal to 1 is equal to 0. So we said we can fold the boundary conditions in. From which we obtain du dx I is equal to 1 is equal to u2 minus u1 over delta x is equal to 0, right? So all we have to do is solve the problem for u1 in terms of u2, which now is going to change the value of the, or the elements of the coefficient matrix. But now, this boundary condition, of course, is a first order approximation, right? This is of order h. So we are basically dropping the orders of the total accuracy of the system, or affecting the global truncation level of the system. So it's no more, even if you're using second order finite differences in the interior, it's no more officially or exactly second order. So there's some degradation of the accuracy close to the boundaries. Or you can use du dx at I is equal to 1 equal to something like, maybe we'll have a ghost point here, okay? Call this I is equal to 0. This is a ghost point. Okay? So then we have u2 minus u0 over 2 delta x of order h squared. Now you retain the accuracy of the system, but now you have an additional equation to solve, right? But you do retain accuracy of the system. The problem is you will not always have a good extrapolated value for quantities outside of the domain. The third one, though, is use higher order one-sided differences. Okay, so I'm going to expand a little bit on this thing and maybe use, again, Taylor series or polynomial approximations to obtain one-sided differences. Then, of course, what then you have is you have a computational molecule, right? Something like this. This is one-sided, high order molecule. Okay, so let's take a quick look at how we do this thing. I don't want to belabor the point, so maybe what I'll do is I'll just write down the important points, but upload these on the web, okay, with my handwriting, but that's okay again. So using Taylor series, we can write f of x plus h is equal to f of x plus h f of x plus h squared over 2 f double prime of x, right, plus h cubed over 6 f triple prime of x with some higher order terms. We can also, if h is small, right, small h, we can also find fx plus 2h. In other words, we have to expand this over a approximate distance of 2h. And this then is going to, again, about the same point, f of x. We can write this as f of x plus 2h, what's that right there? hf prime. I'm missing something here, right? h f prime of x. Okay, so then I have 2h f prime of x plus 2h squared f double prime of x plus 4h cubed over 3 f triple prime of x, again plus higher order terms. And if we call this equation 1, call this 2, multiply 1 by the number 2, okay, not equation 2, and subtract from equation 2. Equation 2, then we get an expression for f double prime x, one-sided, is equal to f I plus 2 minus 2 f I minus 1 plus f I over h squared. So this is a one-sided derivative for the second derivative approximation of order h. Okay, now we're going to use this in the one-sided difference for the first derivative, and we can write f of x plus 2h what's the name there? X, just one second. You know, maybe I shouldn't go into this thing. All right, not x plus 2h, I'm sorry, okay, I made a mistake there. So let's obtain a one-sided, or let's look at f of x plus h. This is equal to f of x plus h f prime of x, right, plus h squared over 2 f double prime of x plus h cube of 6 f triple prime of x, again higher order terms, and solve this equation for f prime of x. From this we can obtain f prime of x as equal to f of x plus h, right, minus f of x over h minus h over 2 f double prime of x minus h squared over 6 f triple prime of x. So that was the whole trick, okay? So for this term, we can substitute from this equation, call this equation 3, okay? Write or substitute equation 3 for f double prime x, okay? From which we obtain f prime of x will be equal to minus f I plus 2 plus 4f I plus 1, right, and minus 3 fi divided by 2h plus order h squared. So this is what I'm trying to get at, okay? So this is a perfectly legitimate way of, writing a first derivative, which is of second order, and you could as well use it in place of the one-sided derivative, okay? And you can also write a reverse or back-sided second-order derivative, f prime of x, that will be equal to f I minus 2 minus 4 f I and fi minus 1, then plus 3 fi divided by 2h of order h squared, and this then would be a back-sided derivative. So in the whole assignment, if you really are concerned about the accuracy of your approximation for the boundary condition, which will have at least one of the boundary conditions as a gradient, then these are definitely two equations that you can use either on the left or on the right side of the problem. You can get exactly the same result by using polynomials, and that's especially interesting and useful if you have a non-uniform grid. Okay, if you have a non-uniform grid, you can distribute the grid points any way you want to, and by taking, say, about 3 adjacent points, you can say I want to pass a polynomial through these adjacent points, and you know the separation between these, and you can fit any order of polynomial into any number of grid points you desire. So suppose we want to use polynomial approximations, okay? For finite differences. Okay, so suppose we want to approximate f of x, right, with a second order parabola or a second order curve of parabola, which is ax squared plus bx, right, plus c. So obviously we need 3 points at which we want to evaluate this function, which is going to give us the values of a, b, and c. Suppose let this curve pass through the following points. We want to pass them through x is equal to 0, h, and 2h. For this purpose, we're just assuming that, again, we have equal distances between adjacent grid points, and you want to evaluate f prime of 0. Now, of course, you can slide the same molecule back and forth and find an approximation to the derivative at different points. So from here, we have f prime of x, right, is equal to 2ax plus b, and then f prime of 0 is equal to c. So for the parabola, then fi is equal to c, right? It's at the center point. Fi plus.
Why is f prime of 0 equal to z?
Pardon me? Well, if x is 0, right? If just 1 second. What did I do there? This should. F prime of 0 should be equal to b. I'm sorry. Okay. This should be b. Yep. This is a b. So I have fi of fi is equal to c, that is the function value. Fi plus 1 is equal to a h squared plus bh plus c. Then fi plus 2 is equal to 4h squared plus 2bh plus c, right? And then solve for f prime of 0 is equal to b, then f prime of b, or f prime of 0 is equal to b. So we have 3 equations, right? And 3 unknowns, c, a, b, and c, which we can solve. For which we obtain this as minus f I plus 2 plus 4i plus 1 minus 3 fi. Oops, I need a f there. This is plus 4f I plus 1 plus 3fi, or minus 3fi, divided by 2h. okay? And again, of order h squared, because we obtain these directly from a fit for a parabola. So you can arrive at the same result either by using Taylor series. Of course, Taylor series generally you have to have an equal mesh between adjacent points. But if you use a parabola, you can fit the parabola, through any arbitrarily distributed spacing or distributed points, which you might want to cluster when the gradients are very high and so forth. Okay. All right. Now, one other thing that we talked about was condition numbers. So I will not really go too much into this thing, but okay. All right. The idea, remember, was that when we have a finite difference equation that we obtain by using second-order finite differences, then the corresponding coefficient matrix is a well-conditioned matrix. Okay, unless there's something very strange in the boundary conditions. So well-conditioned matrix essentially means a condition number is small, and this condition number is a number that is based on some predefined matrix norms. So remember, we talked about the maximum norms, right, as a row sum or a column sum. And then we talked about the L2 norm, which really is the root mean square of the error, right? So you would get probably different values of the condition number in terms of its, mantissa, if you will, okay? But what you really are interested in is the order of magnitude of the condition number. And again, it is very strongly dependent on the processor that you're going to use, and if it's a large bit arithmetic that you're dealing with, in other words, if the significant digits that are represented in the machine, say in a 64-bit machine, versus in an 8-bit machine, right? Of course, that also will affect the possibility of getting a reliable solution, although the condition number might be large for a processor that uses a small number of bits. So let's consider the system AX is equal to B, right? Well, I said F there, okay. F, where A is a matrix that is minus 0.002, 4.0, 4.0. Then I have minus 2, 2.906, minus 5.382, 3.0. I'm going to post these, okay? Minus 4.031 and minus 3.112. And I have an F matrix, F right-hand side vector, which is 7.998 minus 4.481 and minus 4.143. Okay, we apply Gaussian elimination. to the matrix as is. Okay, of course, what you can do is you can do row exchanges and so forth and condition the matrix to a state where the small diagonal does not appear, or the small number does not appear in the diagonal. For instance, if you exchange the first and the third rows, right, then you'll have a diagonal which is, or matrix which is much strongly diagonal content or much higher diagonal content than the original matrix. So when you have small values, right, on the diagonal versus large value, some disparity, large disparity between the values on the diagonal in a given matrix, and you go through a Gaussian elimination, then you run into trouble. So suppose we use Gaussian elimination, and we arrive at a matrix that reads something like minus 0.002, 4.0, 4.0, 0, minus 3.997, and minus 4.005, and then I have 0, 0, 13. So this becomes my matrix equation. There's a point here, okay? And this is x1, x2, x3, and the right-hand side, that would be 7.998 minus 8.002 and 0. Condition number of A, well, this, let's call this, well, the new A, okay, is equal to 2.8 times 10 to the 6, which is a pretty large number. So when you solve this equation, then x will be equal to, x1 is equal to, what was it, 5, 2.02, and 0, and from the solution. But the true solution, x true, is equal to 1, 1, and 1. Okay? So when you invert a, or use a matrix without really conditioning the matrix properly, then the solution will be very significantly off. I looked at MATLAB has a built-in condition number calculator, but I think they are using a different norm that I use. So if you try it on MATLAB, you might get something different, but this value will be about the same, okay? And actually, I calculated this value based on the true values of the A matrix, where one would have 2000, 2906, and 5382 without the. But then what you can do is you can always, of course, take the whole row of the matrix and the right-hand side and multiply it by any constant. As long as you scale them all in the same fashion, the solution, of course, will not change. Okay?
So what do we have to do in order to avoid this wrong solution here?
Well, of course, I'm coming to it, okay? Now, suppose you do row exchanges. Well, first of all, you have to be cognizant of the nature of the matrix, okay? So you have to be sure that the matrix is not a ill-conditioned matrix. Or when you go through a Gaussian elimination or any kind of elimination process, if you start with a matrix which has very small values on the diagonal and large values on some of the diagonals, then eventually you're going to come up with a matrix that's not going to be a well-conditioned matrix, okay? So the best thing really is to look at your solution matrix and find out if it is a matrix where the diagonals are at least on the same order, or this on the same order as the off-diagonal components. Okay. So if we do row exchanges, exchange 1, row 1 with row 2, or row 3, I'm sorry. So what you get is an A matrix that is something like 3.00 minus 4.031 minus 3.112, then minus 0.001, 4.0, 4.0, minus 2, 2.906, minus 5, pardon me?
Did you say you want to exchange 1 and 3?
I'm not, actually that's a good point. I'm simply bringing row 3 to row 1, okay? I'm making row 3, row 1. So I'm not putting row 1 to row 3, okay? So it was 1, 2, 3, so this time becomes 3, 1, 2, okay? They write it properly there. Okay, what shall we say? Make row 1, row 3, row 1, okay? Make row 3 row 1. Does that make sense? Okay. We do that, of course, we have to work with the right-hand side of this equation too, and this will be minus 4.413, right? 7.998 and minus 4.481, the transpose, right? So this is a column vector. So we go through the elimination process, again, using Gaussian elimination.
Is it 4.143 or 4.41?
The last one?
First one.
Oh, whatever it was before, it's the same thing. So what was it? Was it 4 point? Pardon me?
4.143.
Okay, then this is 4.143. Yeah. 4.143, right? Yeah. Okay, that's good. Okay. So again, using Gaussian elimination. Okay, we get an A matrix that reads like 3.0 minus 4.031 minus 3.112, 0, 3.997, 3.998. Okay, 0, 0, minus 7.681, and then F matrix, or F vector, minus 4.143, you were correct, 7.995, and minus 7.681, which then is going to give us x is equal to actual values, very close, 1, 1, 1. Actually, there are no, okay. Okay? So using this very simple idea, it is possible to improve your accuracy rather dramatically. Okay, now generally the way the condition number is calculated from a norm, okay? A matrix norm. All right. So condition A is equal to some matrix norm A. Oops. All right. Times the same norm of A minus 1. Okay? So it needs the inverse of the matrix. So because presumably if A is ill-conditioned, then the value of the inverse will be also somewhat shaky, but generally what you're really looking at is order of magnitude, not the exact values of these things. So this could be a row sum, a matrix norm, or a column sum. Okay? So let me give you an example again. If A is equal to maybe I'm rewriting this thing, but bear with me, okay? 3.02 minus 1.05, 2.53, then 4.33, 0.56, minus 1.78, and minus 0.83, minus 0.54, and 1.47. So the row sum would be 6.6 here, right? If you add all the matrix elements right there. So this is 6.5, no, 6.67. Right. This is 6.67, and this is 2.84. So this is, of course, the maximum norm, right? Maximum row sum. Okay? And the A minus 1 matrix would be something like 5.561 or 5.661 minus 7.273 minus 18.55 and let's say 200.5 minus 268.3 minus 669.9, and this is 76.85 minus 102.6 and minus 255.9, and then the row sums will be 31.48. Then we have 1538.
So when you say row sum, do you mean the square root of the individual component squared?
No, I'm just summing them up.
But then how does the row row sum of the last row become 2.84? That's 0.1 if I do the math.
Maybe I'm missing a minus there. Okay. Okay. So this should be what then? 13. This is almost equal to 0, right? Let's make this. I mean, that definitely is not the highest in any case. Okay. So this will be. I got it wrong there. Okay. Close to 0. Okay.
At 0.1, right?
Yeah, 0.1. Okay. So right here, 6 is 8 is about 9. Just for a second, what did I do here? No. Okay, we're adding these as adding the absolute values here. Okay, I'm sorry, I made a mistake there. Yeah, we're adding the absolute values. All right. So this is correct. Okay. So it's 2.84. 2.84. So these are sum of AI. Okay. So these are absolute values, adding absolute values. The matrix knows, okay, absolute values. All right. So yeah, of course. All right. So this is 5, 12, about 31, 200, 400. So this should be about 1138. 1138. And here we have 435. And so this is the norm of the other one. Okay, a minus 1. So then the condition numbers would then be equal to 6.67 times 1138 times 1138. No, there's no, okay. So this is 6.67 times 1138, which is equal to about 75.95. Okay, so let me give you a definition of the.
Isn't it 7590.5?
75 what? 90.
0.5.
All right. Okay, so it is about, the important thing is this is on the order of 10 to the 4. Okay, so you're not really too concerned about the exact values of these. So you just want to look at the order of magnitude. So this is a large or relatively large number. All right. So the maximum row sum then, maximum row sum, right, then will be equal to A which is given as maximum 1I to N sum over J is equal to 1 to N of Aij. And Aij are the matrix or elements of matrix A. Okay, you could use a column sum, or you could use a L2 norm. L2 norm would be the, well, you could use a column sum or a row sum, but most likely the mantissa will be different, but you're going to get the very similar order of magnitude analysis from these things. Okay? So I'll post a homework not unrelated to the stuff that we talked about today, especially the first part. So you'll definitely get a a problem with an iterative solution of coupled equations, okay? And probably also I'll give you a homework using unequal measure. I post some, reading material on it that you can use. Okay, yeah.
There are some exams next week, so if there's any chance you could be generous with the due date for the next homework, it would be appreciated.
Well, I mean, I can't always make a. I mean, why don't you ask the other class? Well, what exam is that?
Fluids and structures at in-class exam.
All right. Well, let's see how it goes, okay?